Imagine falling from 35,000 feet. The air outside is minus 50 degrees. The metal around you is tearing apart at 500 miles per hour. Within seconds, everything turns into a blinding fireball. Steel melts, concrete shatters, human life vanishes. Yet amidst the smoking crater of a catastrophic commercial plane crash, one single object routinely walks away completely unscathed. It is not black, it is bright, screaming orange. We call it the black box. But what actually happens when you take an industrial diamond tip saw and cut through its multi-layered armor? What does the literal brain of an aviation disaster look like on the inside? Most people think it is just a heavy-duty hard drive. They are dead wrong. Inside this orange cylinder lies a terrifyingly complex masterpiece of survival engineering, packed with specialized microchips, military-grade insulation, and an underwater heartbeat that can scream from the bottom of the ocean for 30 days straight. Today, we are opening one up. We are going past the warnings. We are going inside the most indestructible object known to man. Every modern commercial airliner carries two of these devices. One sits in the electronics bay near the cockpit. The other is bolted deep inside the tail section. Why the tail? Because statistically, when a plane hits the ground nose first, the tail acts as a massive crumple zone. It absorbs the least amount of kinetic energy. It gives the data the highest statistical probability of survival. The first device is the Flight Data Recorder, or FDR. It tracks over 80 different parameters every single second: altitude, airspeed, flap positions, engine thrust, wheel brakes, pitch, roll, and yaw. It gathers up to 25 hours of continuous data. The second device is the Cockpit Voice Recorder, or CVR. It records every radio transmission, every automated cockpit alarm, and every word spoken by the pilots. More importantly, it captures ambient sound. It picks up the subtle click of a faulty switch, the low rumble of a failing turbine, or the sudden, terrifying boom of an explosive decompression. But here is the ironic twist. These machines do not prevent crashes, they record deaths. They are built solely to tell the living exactly how the dead perished. Look closely at the exterior shell. It is coated in a highly reflective, heat-resistant, international orange paint. Why? Because when a team is combing through miles of dense burning jungle or muddy swamp water, bright orange stands out. It screams for attention. Yet, stenciled across the side in bold black lettering are the words, Flight Data Recorder. Do not open. We are going to ignore that warning. To understand the sheer insanity of what is inside, we first have to look at what this outer shell must survive. Before an aviation authority certifies a black box for a commercial flight, the manufacturer has to subject it to what engineers call the Gauntlet of Death. First comes the crash impact test. A pneumatic cannon fires the black box directly into a concrete wall. The force? 3,400 Gs. To put that into perspective, a human being passes out at around 9 Gs. A car crash at 60 miles per hour generates roughly 100 Gs. The black box takes 3,400 times the force of gravity, crushing its outer housing, and it must keep recording. Next is the piercing test. Engineers drop a 500-pound steel spike with a 1/4-inch hardened tip directly onto the unit from a height of 10 feet. It is designed to mimic sharp fuselage debris piercing the unit. Then comes the static crush. A hydraulic press applies 5,000 pounds of crushing force across all axes for 5 full minutes. But the real killer is the fire. Jet fuel burns at roughly 1,500 to 2,000 degrees Fahrenheit. So, engineers place the black box inside a specialized furnace. They blast it with a continuous flame of 2,000 degrees Fahrenheit for 1 hour. Then, they drop it into a secondary chamber heated to 500 degrees Fahrenheit for another 10 hours. Sit with that for a second. 11 hours inside a roaring furnace. If the internal memory chips reach even 300 degrees Fahrenheit, the digital data corrupts. It vanishes forever. The secrets of the crash are wiped clean. So how does the internal machinery survive a temperature that can melt aluminum? Let us start cutting to find out. As the saw bites into the outer casing, the first layer we encounter is the structural housing. This is typically made from a 1/4-inch thick sheet of forged titanium or high-grade stainless steel. Titanium provides the ultimate strength-to-weight ratio. It prevents the box from warping or cracking under those immense G-forces or crushing hydraulic pressures. Once we penetrate the metal skin, we hit the second layer. This is where the magic of thermal protection happens. You might expect high-tech aerogel or complex liquid cooling systems. Instead, you find something shockingly low-tech. Engineers call it dry cavity insulation, but in reality, it is a dense, chalky, clay-like substance or a specialized formulation of castable drywall plaster. One lead aerospace engineer famously called it dumb but completely necessary. Why plaster? Because plaster contains chemically bound water molecules. When the intense heat of a jet fuel fire strikes the outer titanium shell, the heat transfers inward to this plaster layer. As the plaster heats up, the moisture inside begins to boil. It undergoes a phase change, turning into steam. This steam absorbs a massive amount of thermal energy and vents outward through microscopic pores in the casing. This process keeps the inner core at a stable, safe temperature right around the boiling point of water, long enough for the external fire to burn itself out. It is a sacrificial thermal shield. It destroys itself to save the data inside. As we scrape away the white, powdery remnants of the insulation layer, we finally reach the inner sanctum. This is the Crash Survivable Memory Unit, or CSMU. It is a secondary, heavy-walled cylinder made of hardened steel, buried deep within the center of the box. Inside this cylinder is where the high-stakes electronics live. When you slide the inner tray out, you do not see a standard computer hard drive. You do not see spinning platters, magnetic read-write heads, or delicate mechanical arms. A traditional hard drive would disintegrate into metallic dust the millisecond it hit the ground. Instead, you find solid-state flash memory. It looks like a series of small green fiberglass circuit boards stacked neatly on top of each other. Glued directly to these boards are rows of black rectangular microchips. These are highly specialized EEPROM chips, electrically erasable programmable read-only memory. These chips have no moving parts. They are completely silent. They store the digital binary code, the zeros and ones, that represent the pilot's final words and the plane's final movements. But they cannot just sit loose inside the steel cylinder. If they did, the violent vibrations of a crash would tear the chips right off their solder joints. To prevent this, the entire electronic stack is encapsulated. Engineers pour a liquid silicone rubber or high-performance epoxy resin into the cylinder until it completely submerges the circuit boards. Once it cures, it forms a solid, rubbery block. This process is called potting. It seals the microchips in a shock-absorbing waterproof matrix. Moisture cannot get in, salt water cannot corrode the contacts, extreme gravity waves cannot flex the silicon. The microchips become physically one with the box. Think about the precision required here. The data is written to these chips in a continuous loop. Old data is constantly overwritten by new data. When a crash occurs, the power cuts out instantly. The circuit freezes. The last moments are locked in time, suspended inside a block of rubber, wrapped in plaster, encased in steel, and armored in titanium. But what happens if the plane does not crash on land? What if it plunges into the dark, crushing abyss of the Atlantic Ocean? If a black box sinks to the ocean floor, it cannot transmit a GPS signal. Radio waves do not travel through water. They die within a few inches. A satellite cannot track it. A search helicopter cannot spot its bright orange paint through thousands of feet of black ocean water. That is where the final external component comes into play. Bolted to the front of every black box is a small silver cylinder that looks like a heavy-duty flashlight battery. This is the Underwater Locator Beacon, or ULB. The ULB does not use radio waves. It uses acoustics, it uses sound. On the face of the beacon are two exposed metal contacts. When the box submerges in water, the water completes an electrical circuit between these 2 points. This triggers an internal battery, activating a high-output acoustic pulse generator. Every single second, the beacon emits a sharp, high-pitched ping at a frequency of 37.5 kilohertz. This frequency is chosen precisely because it sits far above the low-frequency rumbles of the ocean, above whale songs, boat propellers, and shifting tectonic plates. It is a distinct synthetic cry for help. The sound wave can travel through miles of open water. Search vessels dropping specialized hydrophones into the ocean can detect this ping from up to 2 miles away, even if the black box is buried under layers of deep ocean mud. And it is built to endure. The internal lithium battery is designed to power that acoustic ping continuously for 30 days straight. It gives search teams exactly 1 month to find the needle in a haystack before the heartbeat goes dead. Think about the sheer weight of responsibility carried by this small orange box. When an elite team of investigators stands over the wreckage of a modern airliner, they are not looking at the engines first. They are not looking at the wings. They are looking for the pings. They are looking for the orange. Because contained inside those potted, plaster-wrapped microchips is the definitive truth. Did the engines fail? Was it a software glitch? Or did something happen inside the cockpit? The black box holds the answers that rewrite aviation laws, change engineering standards, and ultimately ensure that the next flight you take lands safely. It is an indestructible vault built on the lessons of past tragedies. But what happens when the recovery teams arrive at the crash site, pull the orange box from the smoking crater, bring it back to the high-security labs of the NTSB, and plug it in, only to find absolutely nothing? What happens when an indestructible machine completely fails? That is a terrifying reality that has already happened, and the mystery it left behind remains unsolved to this day. If you want to discover the chilling story of the flights where the black boxes went completely silent, let us know in the comments. We will dive deep into the anomalies that baffled investigators and the dark secrets that were lost forever. See you there.